Professor R. Ashokamani, Director for Research and Development, Dhanalakshmi Engineering College, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series in applied electronics. Now we are seeing one of the chapters in the paper on physics of materials intended for 3rd semester students of applied electronics. Now we are seeing the second lecture in the chapter on crystal structure. The contents of this lecture are as follows: translational invariance, primitive and compound unit cell. As I told you in the earlier lecture, the crystal structure and bonding, they decide the properties of materials. Now, what do you mean by crystal structure? In order to understand crystal structure, the basic things which you should know are the meanings of the words lattice, basis, crystal structure. Now, this is the lattice, a space lattice. What do you mean by lattice? It is an array of points in space. It is an imaginary network of points in space, an ordered arrangement of points in space which you should visualize. In space, you have a point here, point here, point here, point here. Okay? It is an arrangement of points, an ordered arrangement of points or network of points in space. Then this is the space lattice. Okay? Then with this you add what is called the basis. You see the dotted circle or ellipse which contains 2 atoms or ions, atom A and atom B. They form what is called a basis. In an NaCl structure, in an NaCl solid, what do you have? You have got a Na ion and Cl ion. So the basis contains 2 ions, Na plus and Cl ion, and therefore with every lattice point you have to associate the 2 ions in the case of NaCl. In a monatomic solid like copper or aluminum, there is only one kind of atom. Therefore, with each and every lattice point you have to attach that atom, or at every lattice point you have to put that particular atom. If you have got 2 atoms, then above the lattice point you have to put the 2 atoms or ions, or if you have got 3 or more species like barium titanate or any other thing, aluminum gallium arsenide, in such a case then you will have 3 species, right. Okay. So, the basis along with the lattice gives what is called a crystal structure. Now, I showed you again the vectors A and B, they are called the primitive translation vectors. Why are they called primitive? The fundamental or primitive, the translation vectors means this is a lattice point, right. This is a lattice point. By translating through a distance A, you get at this point, again translating through A, you get this point, translation through A, you are getting this point. Similarly, here what you observe now, translate through E, from this lattice point you go to this lattice point, another lattice point, another. By translating A or by translating B, you get the lattice points here, 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 and similarly in this lattice point, and so on. And this cell, which is made up of A and B, the enclosed area is called a primitive cell, right? It is called a primitive cell, and in a moment I will show what is meant by compound unit cell, right. Now, once again I am showing what is called T. It is called the translational lattice vector. T is equal to U times A plus V times B plus W times C, where U, V, W are integers, right, or N1 times A plus N2 times B plus N3 times C. What are A, B, C? They are the primitive translation vectors. By translating A, B, C N1 times or N2 times, or in 2-dimensional space, you have got 3, 1. What is 3, 1? I have moved from this point 1 times A, 2 times A, 3 times A. Okay, this is 3. That is 3A. T is equal to what? 3 times A plus 1 times B. 1 times B means this point, right. I have moved 1A, 2A, 3A, and then moved from this lattice point to this point along this direction B. So, 3 times A plus 1 times B, it takes me from this point to this point. The beauty of these lattices is the fact that they have translational invariance. What do you mean by translation invariance? There is nothing to distinguish between this lattice point and this lattice point. If I have a person here, I keep his eyes blindfolded, right. I have a handkerchief and I make him to be, I tie his eyes or made to closed by means of kerchief. I am closing the eyes. I am taking this person from this point to this point and to this point and to some other point. Okay, I end up here. From this point I have taken him 1 times A, 2 times A, maybe 3 times A. Okay, this point. Now, if I ask him, the person has come here, if I ask him from where did you start, he will not be able to tell from where exactly he started, because it is infinite lattice. Every point, any point, every point will have identical indistinguishable arrangement of points around that point, because there is nothing to distinguish this between this point and this point. Here, if you take this point, this is surrounded by one lattice point here, one lattice point here, one here, one here. There is this is a surrounded by 4 nearest neighbors, and take some other point, lattice point, 1 here, 2 here, 3 here, 4 here, right. So, there is nothing to distinguish between this point and this point or this point. So, each and every point will appear to be identical. That is the reason why it is called invariant. So, after translation you go back to some point which is invariant to some other point, right. It is called translation invariance. After translation you end up at some point which is in no way different from some other point. Any point, every point, that equivalent, right, equivalent and indistinguishable network of points, right. So, this point if you take in a lattice and some other point that you take in a lattice, now both the points are identical, in the sense there is nothing to distinguish between this and this, they are equivalent points, right. Now, let us look at the unit cells. This is called the unit cell. I mean, you call a primitive unit cell, right. Primitive, you see the lattice point here, lattice point here, lattice point here, lattice point here. You find the lattice points at the corners of the cell. It is called a primitive unit cell in 2 dimensions. Now, what I am going to do is I am going to translate this lattice point, a 2-dimensional lattice showing a translation of a unit cell. The unit cell is translated by a vector R, which will be 3 times A plus 2 times B. I take this cell, I translate it 1 times 1A, 2A, 3A, 1B, 2B. Okay. So, from this point has been taken, this OR will be equal to 1 times A, 2 times A, 3 times A, 1 times B, 2 times B. Okay. So, when I go from this point through a distance 3A plus 2B, I end up at this point. So, this unit cell has been moved from here to here. So, this OFED will become O prime, F prime, E prime, D prime, right. So, all the cells will be identical. It is something like, if you look at the wall is made up of bricks, all blocks will be identical, right. There is nothing to distinguish between one brick and another brick. I will come to the story of bricks later, but now what is the difference between primitive cell and unit cell? A primitive cell is the smallest unit cell which, when repeated indefinitely in 3 dimensions, will generate the entire lattice. The entire lattice can be obtained by translating the primitive cell, whereas a compound unit cell is a one in which there will be lattice points even at the center. You can have a lattice point at the center, it is called a compound unit cell, right. You have more than one lattice point. A unit cell or a compound unit cell is the smallest unit that has all the symmetry elements of the lattice. So, apart from lattice points at the corners, there may be lattice points at the center, that is called a compound unit cell. The important point I want to emphasize here is that the compound unit cell alone will give the symmetry properties of the entire lattice. Again, I should also include the symmetry of the lattice has a bearing on the properties of materials. So, or in other words, the property can be inferred from the symmetry of the lattice. I will say that a piezoelectric crystals should be non-centrosymmetric. I will come to that little later. What I would like to tell you is, a crystal what is piezoelectric, the phenomenon of piezoelectricity will be shown by only those crystals which do not have inversion center, or non-centrosymmetric crystals alone will be piezoelectric. So, there is an intimate relation between symmetry and physical properties. The symmetry properties will be exhibited only by the compound unit cell, but not by the primitive cell. At the same time, it should be borne in mind the entire lattice can be obtained by translating either the primitive cell. A compound unit cell is one in which there may be a lattice, there will be one more lattice point here, right. A lattice point will be here, and so a compound unit cell will also be able to give the entire lattice when it is being translated. So, both the primitive cell and the compound unit cell will be able to generate the entire lattice. All lattice points will come, or the entire lattice can be obtained, but the compound unit cell alone will give all the symmetry properties. The symmetry properties are related to the physical properties, okay. And now I show you the structure of iron, right, and this is a unit cell containing 2 atoms. There is number of atoms equal to 2. How do you get 2? There is one atom at the center of the cube, and you have got 8 atoms at the 8 corners, that they will contribute only 1/8 for a cell. These things we will see in a greater detail in the time to come, but this is called a crystal structure, okay. This is called a crystal structure. One example I am showing is a body centered cubic structure, namely iron, right. Now, let us look at both the primitive cells and the compound unit cells, about which we talked about. From this picture, can you show which are the primitive lattices and which is a compound unit cell? Now, look at A. You have got in the unit cell A, you have got lattice points only at the corners, and similarly some of the cells or the primitive cells. I was showing the cell A wherein you find the lattice points at the corners of the cube. Similarly, B is another cell, right. The point I want to tell you is, by translating A, you will be getting this area, right. By translating this A, again you will be getting this area. The entire lattice can be, or entire set of points can be generated by translating A. Similarly, B is another primitive cell. This primitive cell also can be used to generate the entire lattice. What about C? C also can be used. D can also be used. Okay. F can also be used. Okay. So, you have to tell me now which are the primitive cells. A is a primitive cell, B is another cell, C, D, F are primitive cells. What about G? G is also a primitive cell, right. It has got only one lattice point per cell. How do you define a primitive cell? You should have only one lattice point per cell, right. So, you got 4 here, 4 into 1 by 4 will be 1, 4 into 1 by 4 will be 1. So, there will be only one lattice point per cell. Okay. Now, what about this small a? Small a is not at all is neither a primitive cell or a compound unit cell. The reason being, by translating this A, you will not be getting the lattice, right. You see, A has got a funny shape. By translating A, you will not be able to generate the lattice. So, A is not a unit cell. Then what about B? You got B here. Now, B is a compound unit cell. B is a compound unit cell containing more than one lattice point. Here you got 4 into 4 lattice points, but the contribution to the cell will be 4 into 1 by 4. So, that makes 1. So, the lattice point per cell, if it is 1, it is a primitive cell. Here you have got lattice points at the midpoints also on this axis, on this axis. So, this is a compound unit cell. By translating this compound unit cell also, you can generate the entire lattice. Okay. So, therefore, you should know the distinction between the primitive unit cell and the compound unit cell. And again, I would like to repeat that the compound unit cell alone will have the symmetry of the entire lattice. The symmetry of the entire lattice will be shown only by the compound unit cell, but not by the primitive unit cell. Secondly, the symmetry of the lattice is related to the properties. If you tell me the symmetry of the lattice, you can tell the property, or vice versa. Okay. So, symmetry and the physical properties are intimately related to each other. I will come to that point after a few lectures. Now, the multi-species, I am showing the primitive cell as well as a compound unit cell, in which you have got only single species or only one kind of atom, right. Now, let us go to multi-species. You have got 2 colors or 2 kinds of atoms or 2 ions. It is this is a primitive cell, right. This is a primitive cell having 2 species. This is a non-primitive cell, right, containing again 2 species. Of course, you know that there are 2 species. This is a primitive cell, whereas this is a non-primitive cell. Now, this is a unit cell. What is a unit cell? A building block that can be periodically duplicated to result in the crystal lattice. It is known as the unit cell. By repeatedly translating this, I should be able to obtain the entire lattice. Okay. This is what I am doing, is repeatedly translating this, I am able to get the entire lattice. That is what is called this is a bigger crystal, and this one is the, I can say, the fundamental building block, right. It is a compound unit cell. You see a compound unit cell, you got lattice points in the corners, you got lattice point in the center, a compound unit cell, by repeatedly translating, by repeated operation, you are able to get the entire thing. And now I go to, from one lattice point I move on to another lattice point, okay, by translating this through a distance a. Okay. Similarly, what I can do is I can have along the x direction, I can generate a set of lattice points. So, n 1 times a, I end up from start from here, I go up to this, then I can go along the b direction, this direction also. This I can call as the primitive translation vector b. I can translate this 1 times b, 2 times b, 3 times b, 4 times b, and so on, right. So, I move along the primitive translation vector, this vector b 4 times b. So, I end up at this lattice point, okay. And translational symmetry. So, I told you that every lattice has got what is called a translational symmetry or a translational invariance. By this, what I mean is translation symmetry of the lattice. There exists a set of basis vectors a, b, and c. You got a vector a and a vector b, may be separated by angle alpha. Okay. By translating this, you see, from here to here, from here to here, then you go through from here to this point, or in general through a vector Rn, which will be n 1 times a plus n 2 times b plus n 3 times c. You end up with at some other point. You start from here, you may go along this direction and you may go along this direction. Now, what is there to differentiate between this and this? That is, they are identical and indistinguishable lattice points. Okay. One can go from any location of the lattice to an identical location by following the path composed of integral multiples of vectors a and b, right. This is called translation symmetry. Okay. And you can look at the bricks of any building. Now, I am showing this is after all, a crystal is nothing but it is made up of fundamental building blocks. In a crystal, what is a fundamental building block? It is a unit cell. What is a fundamental building block in a building like this? In any building, the fundamental building block is a brick. Now, if you got a brick here, you got another brick here, you got a brick here and a brick here. You have visualize a brick here and a brick here. And how do you construct a building? You are having a brick and another brick here, another brick here, right? Or you have a brick here of length L, say A, B, C. They are the lattice dimensions or the length, breadth, and thickness of the brick A, B, C. By translating the brick, by placing the brick one over the other, you are constructing the wall. Every brick is, every region is identical. Okay. Then what do you have between bricks? You know, you cannot have a building by having bricks alone. You have got some cementing, right. Cementing is the bonding. Let us have a look at this building. This building is made up of bricks. What I would like to tell you is this brick, then you have got adjacent brick here, adjacent brick here, and how do you build this whole structure? By stacking bricks one over the other, right. You are stacking bricks, right. So, or in other words, you have got a brick here, brick here, brick here. By translating the bricks, right, in all the directions, along x direction, then y direction, then the thicker the wall along the z direction, you are getting a wall of this much thickness, then the whole structure is obtained. Similar to the building, the construction of the building, a crystal or a material is built by translating the unit cell. What is a unit cell? In a wall, the brick is the unit cell, right. So, the point I would like to emphasize is the brick forms the unit cell of a wall or a building. Okay. And there is nothing to distinguish between one brick and another brick. By translating the bricks, by stacking the bricks one over the other, you are constructing the building. Similarly, by stacking the unit cells, you get the crystal structure. This is a beautiful building, and you have got another beautiful building, right. So, when you go near the wall, you can enjoy the beauty of the translation invariance can be obtained. You cannot distinguish between one brick here and another brick here, and this brick and this brick will be identical. When you have a brick here, that will be surrounded by the same number of bricks as you have got another brick here. This is the College of Engineering, Guindy, from the prime seat of Anna University, from where the lectures are being presented. The bricks make the building. The idea of talking about this building is a crystal is made up of unit cells. The unit cell is the fundamental building block, and similarly here the brick is the fundamental building block. Okay. Let us go to 3-dimensional solids or 3-dimensional solid structures. Now, so far I was showing you a 2-dimensional lattice. In a 3-dimensional lattice, it is nothing but a spatial arrangement of atoms representing a periodic lattice. Now, this arrangement is invariant with respect to TR, where R is an integer linear combination of 1, 2 or 3 primitive vectors. The primitive vectors are u1, u2, u3. As I told you just now, you can have n1, n2, n3 are the 3 integers, a, b, c are the lattice constants, au1, bu2, cu3 are the translation. So, there are 6 parameters that define the unit cell of a lattice, right. In general, you can call this as the unit cell of any lattice. What are the 3 important variables? The lattice parameters a, b, c, where do you find? This is a here, this is b here, and c here. Okay. Something like a brick, you have got every brick has got a length, breadth and thickness a, b, c. The brick will have the 3 dimensions, length, breadth and thickness. You know, in a brick the angles are exactly 90 degrees, right. Okay. But here the angles in a unit cell, out of which the entire structure is formed, a solid structure is formed or solids are formed, there may be a cadmium will be crystallizing in hexagonal close packed structure. So, there will be hexagons. So, the angles alpha, beta, gamma, they will not be equal, right. Then we have to talk about symmetry operations. Now, let us go to the summary of today's lecture. All lattices have the property of translational invariance. Both primitive and compound unit cells can be used to generate the entire lattice. Compound unit cell alone will exhibit all the symmetry properties of the entire lattice. Let us pass on to the part on questions. You have the following questions. What is a symmetry operation? How do you define rotation symmetry? With this we come to the end of the lecture 2. The rest of the things we will see in the lectures to come. Thank you.